All right, calculus students, we pick up with the calculus of logarithmic functions. Just to be clear, I'd just maybe add one example to what we just looked at. Suppose you have the function f of x is equal to 3 to the 4x squared. Well, if you notice, it's not e to the 4x squared. And the only difference in that situation, it's really not a big deal. Just you have 3 to the u and you have 4x squared. Using the chain rule here, the derivative of 4x squared is 8x. The derivative of 3 to the u is 3 to the u times the natural logarithm of 3. So you just attach the natural log of the base. You multiply that out, you do get 8x times 3 to the 4x squared times the natural log of 3. So that's the derivative in that situation. So you have a different base than e, just attach on the natural log of that base. So what is a logarithmic function? So we talked about an exponential function looking like this. So a logarithmic function looks like that. Okay. So this is e to the x. This is the natural log of x. If you notice, the one function is the same as the other flipped over the line y is equal to x. That's because they're inverse operations of each other. For example, suppose you wrote this expression. Say 8 was equal to 2 to the third power. Well, as a logarithm, we would write log base of 2 of 8 is equal to 3. So those expressions mean the same thing. The graph is expressed like that, and logarithms have these interesting properties about them. For example, suppose you had the natural log of x, y. Well, that's the same thing as the natural log of x plus the natural log of y. Suppose you had the natural log of 8 divided by z. That's the same as the natural log of 8 minus the natural log of z. And suppose you had the natural log of 2 to the third. Well, that's the same thing as 3 times the natural log of 2. So from your college algebra class last year, logarithms, those were some important relationships that we discussed. And so there's a little bit of a review that we'll be referencing during some of these examples. So what is the derivative of the natural log function? It's 1 over x. Works out very nicely. And if you have a different base, the derivative of a log with a base of b of x, it is simply 1 over x times the natural log of b in the denominator. So we're going to find the derivative of these two functions. And I'm going to actually do it two different ways. The first way is to write it using the chain rule. Notice I have the natural log of u, and then I have 1 over x squared, or x to the negative 2. The derivative of x to the negative 2 is negative 2 x to the negative third, or negative 2 over x cubed. The derivative of natural log of u is 1 over u. So notice what I get. In this situation, I have 1 over x to the negative 2. So that comes to the top, or x squared, times negative 2 over x cubed. Notice that the x's will cancel, and I get negative 2 over x. That's the derivative. I'm in fact going to show you another way of finding this derivative. F of x is equal to, and in this case, we have natural log of x to the negative 2. Using my properties of logarithms, I could dump this on the outside. So I have f of x is also equal to negative 2 natural log of x. Now, instead of using the chain rule, I can simply find the derivative using my properties of logarithms. It's negative 2 over x, because the derivative of natural log of x is 1 over x. Works out quite nicely. This one, f of x equal to log base 4 of e to the 2x. So I set it up. I have log base 4 of u, and I have e to the 2x. The derivative of log base 4 of u is 1 over u times the natural log of 4 in the denominator. The derivative of e to the 2x, I wonder if you've caught on to this by now. E to the u and 2x, derivative is 2, derivative is e to the u, so I get 2e to the 2x. Notice we don't even really need to make this so much anymore. Hopefully you realize by now that in order to find the derivative, when you have e to a power, you take the derivative of the top and just stick it in front. So it's 2e to the 2x. When you multiply these together, you get 2e to the 2x on top, and on the bottom, you get e to the 2x times the natural log of 4. Notice how the e to the 2x is canceled, and I get 2 over the natural log of 4. Works out quite nicely. What about the natural log of x over e to the x? If you said to use the quotient rule, you are correct. The derivative of the top is 1 over x. The derivative of the bottom is, or the bottom is just e to the x. Minus, the derivative of the bottom is e to the x times the top, natural log of x. All over e to the x squared, or e to the 2x. Notice you can factor out an e to the x out of the top, and it will cancel with the bottom. So I have 1 over x minus natural log of x over 1 divided by e to the x. I'm going to multiply the top and bottom by x so that I have common denominators. And I get 1 minus x natural log of x over x divided by e to the x over 1. When you multiply by the reciprocal, notice that you get an e to the x in the denominator. That's my derivative. Letter D looks extremely complicated, and it is not. The reason why it looks extremely complicated is it looks like you would set up the use of the chain rule. You don't have to write this down because I'm going to change the problem a little bit so it's a nicer problem for you. This should say f of x is equal to. If I were to write the chain rule, I'd say the natural log of u, and then the inside would be this thing right there. And then I would have to use the product, and I would have to use the chain rule. And so you would have the chain rule with the product and the chain inside of it twice, 4 different rules, a lot of work, and we can actually avoid that. Some people get really impatient during this time as they're looking at this derivative. If you just hang on and just say, you know what, I'm going to trust that I can figure this out, you're going to be just fine. There's a really easy way of working through this derivative. If we need to go over in class again, we sure can. But I notice that these are being multiplied together. And one property I've learned is that I can take logarithms of a product and separate them using addition. So notice I haven't written the derivative. I've just rewritten f of x. I'm going to do that again because I've also learned that you can take that exponent and dump it out front when you have a logarithm. So I get 4 natural log of x plus 2 plus 10 natural log of x minus 3. Now I take the derivative of each, and each will require the use of the chain rule, but a lot less complicated. Watch this first one, 4 natural log of u and x plus 2. The derivative of 4 natural log of u is 4 over u. The derivative of x plus 2 is 1. And so therefore, when I multiply those together, I get 4 over x plus 2. That's the first derivative. Plus the next derivative 10 natural log of u and x minus 3, the derivative of 10 natural log of u is 10 over u, and the derivative of x minus 3 is 1. Multiply those together, and I get 10 over x minus 3. That's a lot easier than the route that we were considering. I'm going to give you a chance to do that again for letter F. But first, let's go to E. For E, there's no way around it. We must set up the use of the chain rule. We start by taking u to the 1/2. And on the inside, we have the natural log of 2x minus 1. Can't separate subtraction. Well, we do know the derivative of u to the 1/2, 1 over 2 roots of u. In order to find the derivative of natural log of 2x minus 1, we set up the chain rule. We have the natural log of u, and we have 2x minus 1. The derivative of the natural log of u is 1 over u, and the derivative of 2x minus 1 is 2. Multiply those together, and I have 2 over 2x minus 1. Notice now as we multiply these together, the 2's will cancel, and I have 1 over 2x minus 1 times the square root of the natural log of 2x minus 1. That's my derivative. Letter F should say f of x as well. Notice we have division. And when you have division, you can go ahead and rewrite the function in 2 parts. Again, I'm not going to take the derivative yet. I'm simply going to rewrite it. Natural log of x minus the natural log of x squared minus 2x plus 4 to the 5th power. So no derivative, just rewriting it. I'm going to rewrite it again. Natural log of x minus 5 natural log of x squared minus 2x plus 4. Now we go ahead and take the derivative. The derivative of natural log of x is just 1 over x. For the second part, we set up the chain rule. We have 5 natural log of u, and u is x squared minus 2x plus 4. The derivative of x squared minus 2x plus 4 is 2x minus 2. And the derivative of 5 natural log of u is 5 over u. As we multiply those together, we get 10x minus 10 over x squared minus 2x plus 4. That is my derivative. A lot easier than setting up the chain rule with the quotient rule with the chain rule again. So I encourage you to rewrite those logarithms as much as you can. In this case, we can't rewrite the logarithms. The reason why we can't is because it's not one logarithm. It's 2 logarithms. We have one in the numerator, we have one in the denominator. There's no 2 ways about it. The only way to do this problem is to set up the chain or the quotient rule. Fortunately, it works out quite nicely. The derivative of the top is 5 over x times the bottom, 4 minus 2 natural log of x, minus the derivative of the bottom is negative 2 over x, so plus 2 over x, times 5 natural log of x plus 3. All divided by the bottom squared. Now, we should combine our like terms in the numerator. As you notice, as we have f prime of x, we get 20 minus 10 natural log of x over x plus 10 natural log of x plus 6 over x, all over 4 minus 2 natural log of x, quantity squared, I'll write it over 1. As you notice in this situation, the negative 10 natural log of x and the positive 10 natural log of x do cancel. 20 plus 6 is 26. The denominator is x, and when you multiply by the reciprocal, you get 4 minus 2 natural log of x quantity squared in the denominator as well. And that is your derivative. So, some good problems. The big key to remember is that the derivative of the natural log of x is 1 over x. This will be 99% of the time you'll be using that derivative. Only 1% of the time will you use that. Same thing as you look above for the previous problems. 99% of the time you'll be seeing the derivative of e to the x is e to the x. Only 1% of the time will you see that form, which is why we practiced it the way we did. Good luck. You are almost home free with all of your lessons. Just one left.